Okay, we're in section 7.4 where we're going to evaluate logarithms and also be able to graph logarithmic functions. Now, the definition of a logarithm is being able to incorporate what is called base b. Base b is a number, and if we let b and y be positive numbers, as long as b does not equal 1, so that means b must be larger than 1, the logarithm of y with base b is denoted as log base b of y. So this is a logarithms. Its definition is what is considered the inverse of exponential functions. So if we had a standard form of exponential functions such as b to the x equals y, that can be rewritten in logarithmic form as log base b of y equals x. So there's going to be some things in your homework where we're going to ask you what the logarithmic equation is and put it to standard form, and sometimes vice versa. So if I have these examples here where I have log base 5 of 625 equals 4. If I'm going to write that into standard form or exponential form, I have to kind of look at my chart here. So I see that my b here is also my base and my exponent. So this one's going to be 5, and then x here's the exponent, but x here's the result. So the result here is 4, so this must be 5 to the 4th power, and so that must equal 625, which is a true statement. And so if I go to b, if I'm going to write this in standard form, I'm going to go 29, which is my b, to the 0 power equals 1, which holds true. Here for c, I got 121 to the 1/2 power equals 11, which is also true. For these examples, I want to evaluate the logarithms. It says without using your calculator. And so basically what it means is we really don't have an x here, so it's like this equals x, and this equals x. So that's what we were trying to say to evaluate it. So we need some variable to help us solve it. So I got 4 to the x power equals 256. So if I kind of go up the chain of exponential, so 4 to the 1 power is 4, 2 is 16, 4 to the 3rd power is 64, and then 4 to the 4th power, well, that's 256. So that means that when my x is 4, this becomes 256, which then holds true. So for b, if I got 15 to the x power, that equals 15. Well, the only way that for that to be true is x must be 1. Here I have, so I got 50x equals 1. For that, my exponent must be 0, because anytime your exponent is 0, that will equal 1. For d, I have to rewrite it as 32x equals 2. So this is where it kind of gets a little bit tricky, because we have a value base 32, which is a larger than our result of 2. So that means that our exponent must be a fraction that's in between 0 and 1. So that means we're going to take the root of something. So what I need to know is what root of 32 will give me 2. And in this case, x will equal 1/5. Because if it helps you out, if you take 2 to the 5th power, that gives you 32. So that means if you take 32 to the 1/5 power, that'll give you a 2. So if you kind of use that, take that mindset, if you kind of reverse the fields there and try to create an environment so you can solve problems that way. For e, my base here will be what? 1/9 to the x power equals 9. So here you have a fraction to some exponent that will give you a whole number. Automatically that should register a negative number. So here, what negative value will work to give you, so like let's take 9. So what exponent of 9 would have to give you 1/8? Well, we know that if you take a negative exponent of something, it's just 1 over that number. And so since if I can take x equals -1, so if I have 1/9 to the -1 power, so I'm just flipping my fraction. So that would make my 9 into the numerator, which then would equal 9, just like on the right-hand side of my equal sign. Okay? So this is kind of what the basis for logarithms, and it breaks down into two common. We got common logarithms where our logarithm is at base 10 and is just denoted as log of b. So anywhere we've been having like log of 5 is 25, something kind of like that. So that means that our base is 5. Anytime you see like something that looks like, oh, it's just log of 25, we automatically assume that our base is 10. That's what it's kind of like when we have a variable. When we have like x plus 3, we just know that it's x to the first power. We don't have to write it. So anytime we don't write what the base is for log, it's just 10. And that's what is shown on your calculator. So if you see a term that just says log on your calculator, that log is just for log base 10, not for any of the other ones. Natural log means that we have a logarithm with base e, which is denoted as called the natural log. So we can say that log e of x will equal the natural log of x. So keep that in mind. That'll help you out with solving some problems. So for a and b, all I want you to do is punch it into your calculator, and you should have a log button, and you should also have a natural log button. So this is log, and that's what natural log. Those is what it should look like inside of your for your calculator in order to solve it. So if I wanted you to round to the nearest hundredth, the log of 7/4 is about 2.4, and the natural log of 6 is 1.79. Talking about inverses of logarithms in exponentials, like I said, both of them together are inverses of each other. And like what we talked about in previous sections, if we use compositions in order to solve inverses, we just get the value of the variable, which in this case is x. So if we have g of f of x equaling the log base of b of x, that will end up equaling x. Same thing goes for if we have f of g of x, which equals b to the log base b of x. That'll also equal x. That's kind of just how that's how inverses work when you use compositions of one another. So if we use that property to help us solve these expressions, this will help us out when we're simplifying. The main thing we have to take note is that this value here and this value here must be the same number. As long as they're the same number, we can solve it that way. If it isn't, we have to manipulate those numbers to create a statement that'll hold true for each individual function. So here I have log base 4 of 4 to the x power. So that our a looks a lot like this equation here. So my b is represented as a 4, and then my x is represented as an x, and then it ends up equaling x. So then my simplified expression here is x because of the corresponding relationship. For b, it looks a lot like this equation, where b is 6 and my x here equals 5. So if I was to simplify this expression, I would say that my answer would end up being 5 because my I'm just substituting in those values into my inverse function. Looking at C and D, the difference between the two of them is that this value here and this value here are not the same. But we can manipulate using exponents, which allows them to be the same. So I have log base 25. I need this value to be 25. But what can I do in order to get an exponential function? What exponent do I have to use in order to make that 1/5? So I know that to make this 1/5, that I know the exponent has to be negative. Because then, let's say if I use -1, that means that my 25 to the -1 power would just be 1 over 25. But now I need 5. But I do know that the square root of 25 is 5. So I'm thinking that if I take the -1/2 power of 25, I should get 1/5. And in this case, I do. But now I still have an x there, and so I write that in. But now I can use the power of power rule to say that log of 25, log base 25 of 25 to the -1/2 x power here, and if I simplify this, my answer will come up to be -1/2 x. So that's my simplified expression. Looking at example D, I have log 2, but I need to get 2 here. So I need to use an exponent that's going to get me 2 to some power is going to equal 32. That value is 5. So if I take 2 to the 5th power, that'll give me 32, all of which is to the x power. So I got log base 2 of 2 to the 5x. And using my formula here, my simplified expression should be 5x. Looking at just finding the inverse of the function itself, what we can do is we can use same rules as we did when we were using inverse functions when it came to solving for any type of quadratics or linear functions. What we're going to do is you're going to flip your x and y values, and then you're going to solve for y. So here, all I'm going to do is I'm going to put this x equals 7y. So the inverse of y equals 7x is x equals 7y. But now what I need to do is I need to solve for y. In order to do that, I must use logarithms, because if we go back, we remember that log base b of x equaled y. So that means that all I got to do is put in log of my b here is 7, my value here is x, and then that equals y. So my answer is log base 7x equals y, and that's the inverse of y equals 7x. If I see something that's y equals the natural log of 3x minus 10, what I want to do first is I'm going to, again, flip it. Let's go x equals natural log of 3y minus 10. Okay. So what if, but now let's recall that, remember what the natural log of x was? This ends up equaling the log base e of x. So I'm going to rewrite that. So let's put down e. Actually, before I do that, let's not flip it. Let's do the log base e of 3x minus 10. Let's do that first. So then when I flip this, it becomes x equals log base e of 3y minus 10. And so now I can say that this is e to the x equals, so what, 3y minus 10. And solving this for y, so I got e to the x plus 10 equals 3y, and I have e to the x plus 10 all divided by 3 equals y. Okay? Last thing I want to do is talk about graphing logarithmic functions. And this is kind of where I'm going to show you how that they're inverses. So the graph on your left is going to show you both exponential function and logarithmic functions when b is greater than 1. So I'm going to make a green graph that shows exponential functions. This is what we had talked about in previous sections here in chapter 7, where we have exponential growth because b is greater than 1. And so now I'm going to make a red graph, and this is what is kind of the standard form for logarithmic functions. So, and what makes it so much different is with exponential functions, like when we talked about asymptotes, for exponential functions, our asymptotes were the x-axis. For logarithmic functions, our asymptotes are the y-axis. And the domain and ranges changes. So like when we talked about how in exponential functions, domain was all real numbers, and then for the apparent exponential function, our range was y must be greater than 0. Well, it's flipped here. Here, our range is all real numbers, which is our y terms, but our domain is the one that has to have some restrictions to it because our x must be greater than 0. That's where the change comes in, and that's why they're inverses. So if I were to show you, let's make a green one of looking at the graph on our right, I want to show you what let's see here, the exponential decay looks something kind of like this. Well, that's a crappy graph, but anyway. And then show you a red one. This is what the red one is, what the logarithmic function is when b is in between 0 and 1. Same thing about the asymptotes, and same rules apply for domain and range. So if I'm going to graph these functions, I want, again, just like we did in other previous sections, I want to make a t-chart and plot some points. But what we've been doing is we've been taking x values and finding y. Here, I want you to make up y values and find x. So the values that I want you to take are, say, 0, 1, and 2. And what we can do is I want to rewrite this in standard form. So let's rewrite it in standard form. So if we're going to write this in standard form, this would become 3y equals x. So if my y was 0, my x would be 1. If my y was 1, my x would be 3. And if my y was 2, my x would be 9. So I'm going to plot these points. So I got 1 comma 0, I got 3 comma 1, and I got 9 comma 2. So from here, knowing that this b is greater than 1, I know the general term of my sketching my graph, so now I can plot these points and then kind of connect them, and then this is kind of what my graph for the log base 3 of x should look like. So now if I look at domain and range here, so my domain, x must be greater than 0, and my range is all real numbers. Here, I have the same thing as we were talking about with translations. Translations here have not changed. This is still h, and this is still k. But what we're going to do when I work on my plotted points, all I'm concerned with is the function that doesn't have h or k in it. So all I'm concerned about is the log base 5 of x. So that's what I'm going to make my t-chart with. All right, I'm going to use 0, 1, and 2. So I'm going to rewrite this as 5y equals x. So if my 5 is 0, my x is 1. If my 5, or I'm sorry, if my y is 0, my x is 1. Excuse me. And then if my y is 1, my x is 5. And if my y is 2, my x is 25. So plotting these points, I got 1 and 0. I got 5 and 1. Oh, so 1, 2, 3, 4, 5. And then I got 25 and 2, so that's way out here somewhere. But now what I can do is now I have points where I can do my horizontal and vertical shifting. Here, my h equals -2, and my k equals -3. So that's telling us that we must move it to the left 2 units and down 3. So I'm going to go to this value here. I'm going to go 1, 2, 1, 2, 3. Plot that point, and I got 1, 2, 1, 2, 3. Plot that point right there, and it's somewhere. So I'll just go 1, 2, 1, 2, 3. So I'll just plot it somewhere close to there. So if I were to make this graph, it would look something kind of like this. Okay. And then if I had my domain and range, so again, the range is all real numbers. But if you remember when we were talking about exponential functions and when we had the translations, I told you guys that k was going to determine what that range was going to be. Well, when we come to logarithmic functions, what's going to dictate where our restrictions are going to be is what our h is what is. And here my h is -2. So my range of values of x, my x must be greater than -2. Okay? And that is solving or evaluating logarithms and being able to graph logarithmic functions. Hope this helps. Until next time.